Everything you think you know about physics, all those neat equations that describe the universe, from a falling apple to a swirling galaxy. Well, they all work until they don't. There's a place in the universe, a point so extreme, so bizarre, that our entire understanding of reality simply shatters. It's where the laws of nature go to die. So, where is this place? Let's dive in. For centuries, we've built this incredible framework called physics. It's a set of rules that governs everything. With it, we can predict the orbits of planets, understand how stars burn, and even map the expansion of the entire universe. But here's the secret physicists don't always advertise. All our laws are just really good approximations. They are descriptions of reality that work beautifully under normal circumstances. But what happens when circumstances aren't normal? What happens when they become extreme? Think about it. Our equations handle big things, fast things, and tiny things. But what happens when something is infinitely big, or infinitely dense, all crammed into an infinitely small point? That's where our rulebook gets tossed out the window. This isn't just a small error or a rounding mistake. It's a fundamental breakdown. The universe is telling us, your math doesn't work here anymore, and that's precisely what happens at the heart of every single black hole. Welcome to the singularity. It's a word we hear a lot, but what does it actually mean? Imagine taking a star many times more massive than our sun and crushing it down, and down, and down, past the size of a city, past the size of a marble, until it's compressed into a point with zero volume. That's a singularity. At this single point, the density becomes infinite. All that mass is packed into no space at all. The very fabric of spacetime, the stage on which the universe plays out, becomes so warped and curved that it essentially collapses in on itself. And perhaps most mind-bending of all, time itself stops making sense. The forward march of moments, from past to present to future, just breaks. Our equations, when we try to apply them to a singularity, spit out nonsense infinities, division by zero. It's the mathematical equivalent of a computer crashing. It's a place where reality, as we know it, ceases to exist. So, why does physics fail so spectacularly here? Why can't our best and brightest theories handle it? Well, it's because the two great pillars of modern physics have a massive fight inside a singularity. On one side, we have Einstein's general relativity. This is our theory for the big stuff: gravity, planets, stars, galaxies, and the curvature of space-time. It works flawlessly on the cosmic scale. On the other side, we have quantum mechanics. This is our theory for the small stuff: atoms, particles, and the weird, probabilistic rules they follow. It's the most successful and accurate theory humanity has ever devised for the micro-world. Normally, these two theories operate in their own separate domains. Relativity deals with the vast and heavy, while quantum mechanics deals with the tiny and light. But in a singularity, you have something that is both. It's incredibly massive, so relativity should apply. But it's also infinitesimally small, so quantum mechanics should also apply. And when you try to use both theories at the same time, they give you completely contradictory answers. They just can't agree. Both can't be right, which means our fundamental understanding of the universe is incomplete. The weirdness doesn't just happen at the singularity itself. It starts as you get close, near the edge of the black hole known as the event horizon. This is the point of no return. As you approach it, some truly bizarre things happen to space and time. From the perspective of an outside observer, your time would appear to slow down dramatically. If you hovered just outside the event horizon for a few minutes, centuries or even millennia could pass for the rest of the universe. Time is stretched to a near standstill. At the same time, space gets warped in the opposite way. The direction toward the singularity, which used to be just a direction in space, transforms. It becomes the future. It's not a place you can choose to go or not go. It becomes an inevitable moment in time that you are falling towards. What was once time, the forward flow of moments starts acting like a spatial dimension. It's as if the roles of time and space literally swap. The fundamental structure of cause and effect, the idea that one thing leads to another in a clear sequence, completely collapses. The ultimate challenge with singularities is that we can never, ever directly see one. The event horizon of a black hole acts as a perfect one-way membrane. Matter and energy can fall in, but absolutely nothing can come out. No light, no radio signals, not a single scrap of information. It's sealed off from the rest of the universe. This is why it's called a black hole. It doesn't emit any light. So, everything we know about singularities is based on inference and the predictions of our theories. We see the effects of black holes on the stars and gas around them. We see the immense gravitational pull. We've even detected the gravitational waves from black holes colliding. These observations confirm that our theory of relativity is stunningly accurate right up to the edge. But what lies beyond that edge, at the core, remains a complete mystery, forever hidden from our direct observation. It's like trying to understand the engine of a car. It's by listening to the sound it makes, without ever being able to lift the hood. So, are black hole singularities the only place where physics might break down like this? Well, they are certainly the most famous and well-established example. But scientists speculate that similar conditions might exist, or have existed, elsewhere. Take the very beginning of the universe, the Big Bang. Our theory suggests that the entire observable universe was once compressed into an incredibly hot, dense point of primordial singularity. Just like with black holes, our current laws of physics can't describe that initial moment. We can run the clock back to a tiny fraction of a second, the Big Bang, but at time zero, the math fails. Other potential locations could be the cores of neutron stars, which are almost dense enough to collapse into black holes, or perhaps even inside hypothetical structures like wormholes, which would also involve extreme warping of space-time. But for now, the singularity inside a black hole remains the most concrete, extreme, and baffling example of where our physics hits a dead end. Now, you might think that finding a place where all our knowledge fails is a bad thing, a sign of defeat for science. But for physicists, it's the exact opposite. It's thrilling. A failure like this isn't an end point. It's a giant, flashing neon sign pointing the way forward. It tells us that our understanding of the universe isn't finished. There's something more, a deeper layer of reality that we haven't uncovered yet. These breakdowns are clues. They are the breadcrumbs that will lead us to the next great revolution in physics. The fact that relativity and quantum mechanics clash inside a black hole tells us that they must be two sides of a more fundamental, unified theory. Finding that theory is one of the biggest goals in all of science today. It's not about being wrong. It's about discovering how to be more right. This search for a new theory is what keeps physicists up at night. They are hunting for something that can handle the extreme gravity of relativity and the bizarre rules of the quantum world all at once. The leading contender is a concept called quantum gravity. There are different approaches to it, like string theory, which suggests that all particles are just tiny vibrating strings, or loop quantum gravity, which proposes that space-time itself is made of discrete, indivisible chunks. These theories attempt to create a new rulebook that works everywhere, from the largest galaxies down to the heart of a black hole. They might involve new dimensions of space we can't see, or a completely new understanding of what time and space even are. The goal is to find a single, elegant theory, a theory of everything, that doesn't break down, that doesn't give us infinities, and that can finally explain the singularity. So, the universe has a boundary, but it's not a boundary in space you can fly to in a rocket. It's a boundary in our understanding. The singularity represents the current edge of human knowledge. It's the place where nature itself stops explaining itself in the language we've learned so far. It's a question mark hanging at the center of a black hole and at the very beginning of time. And until we find that new theory, that deeper level of physics that can make sense of the infinite, That point will remain the ultimate frontier. It's where the map ends, and where the greatest adventure in science is just beginning. Thanks for exploring the edge of reality with us. If you enjoyed this journey into the unknown, be sure to like this video and subscribe for more deep dives into the cosmos. See you next time.